Hi, my name is Mike Sullivan. I'm from the Architecture Research Group at NVIDIA, and I'm going to talk to you about characterizing and mitigating soft error effects in DRAM, with a focus on the HBM2 and current compute class GPUs. GPUs are being used in many high reliability applications, including high performance supercomputers, data center and cloud systems, and autonomous driving systems. DRAM is the largest and most susceptible memory in a GPU, and so these high reliability GPUs protect DRAM with error correcting codes, or ECCs. ECC is used to avoid the risk of silent data corruption in the presence of random hardware errors such as soft errors that may be caused by terrestrial radiation. Soft errors are non-destructive events, but their impacts can be problematic and long-lasting. In the event of a soft error in DRAM, typically one of the three following things occurs. The error may be detected and corrected by the ECC, avoiding any ill effects. This, of course, is our intended result. But there is also a chance that the error is detected by the ECC, but it is unable to correct the erroneous error pattern. In this case, a detected yet uncorrected error, or DUE, is reported to higher levels of the system, which results in an error-related crash. Finally, the most problematic result is that the error may escape the ECC and result in silent data corruption, or SDC. This can threaten the validity of computation, and avoiding SDC is our most pressing goal when designing an ECC scheme. To get the highest percentage of corrected errors and the lowest SDC risk, ECC should be tailored to the most prevalent soft error patterns. This talk describes how to characterize and mitigate soft errors in HBM2 DRAM. We use neutron beam testing, which is a methodology to observe soft errors at highly accelerated rates. Neutron beam testing is the gold standard for soft error characterization, and the results in this paper come from the ChipIR facility in the UK, whose neutron energy spectrum is tuned to closely resemble that of the terrestrial environment, but with hundreds of millions times more neutrons per square centimeter per second. To perform our experiments, we run a specialized microbenchmark in the radiation beam that monitors and logs soft errors, and then we post-process these logs to guide ECC code design. The first finding of our HBM2 error pattern characterization is a relatively high error breadth and severity. In this talk, I use the term breadth to describe the number of memory entries affected by a single event, and severity to describe the maximum number of erroneous bits across all affected memory entries. This slide shows the soft error patterns we observe, broken into four classes. SBSE, or single bit, single entry errors, affect only a single isolated bit. This is the most common single error pattern and is easy to correct using ECC. While single-bit errors are the most common pattern, multi-bit errors are much more important to focus on due to their high breadth and severities. Multi-bit errors exceed the correction and detection capabilities of a single-bit error correcting code. If they occur, they can cause an error-related crash if you're lucky enough to detect the error, which is not guaranteed. But even more problematic is the other case where ECC fails to detect a multi-bit error, or it erroneously miscorrects a non-faulty bit, further increasing the error severity. This case results in silent data corruption despite ECC protection. One other finding from our data is that the breadth of multi-bit, multi-entry errors can be quite broad. We call these errors NBME errors for short. The number of entries affected by each NBME event is shown on the left in a histogram with increasing bin sizes. NBME errors with thousands of erroneous entries are common, which further demonstrates the potential multi-bit SDC risk from these broad and severe errors. Luckily, the errors we observe are generally structured, meaning that we can potentially tailor our ECC to detect or even correct most multi-bit errors in the field. The single most prevalent structured error pattern we observe is the prevalence of errors that affect at most one logically contiguous byte per memory entry. We call this type of error a byte error, for short in this talk. Almost 3/4 of the observed multi-bit errors were byte errors. Among the remaining quarter of non-byte aligned NBME errors, we generally observe wholesale corruption in the entire memory entry, such that all 32 bytes can be affected in a single HBM2 memory transaction. We ultimately boiled down the error patterns and probabilities into a simple analytical model with the following 7 error classes. These errors are shown in roughly increasing difficulty for ECC-based correction and detection. Single-bit errors affect an isolated bit of DRAM. Pin errors can affect up to all 4 bits coming from a single DRAM pin. Byte errors affect at most all 8 bits of a single byte, and arbitrary double and triple bit errors are uncommon, but they do occur. There are also single beat errors that can affect up to all 64 data bits in a single DRAM beat, and then whole entry errors, which can affect up to all 256 bits in an HBM2 memory transaction. The prevalence towards byte errors makes some intuitive sense if you look at the structure of DRAM. DRAM is deeply hierarchical. For example, an HBM2 stack is composed of DRAM dies, which are made of channels, which are composed of banks, which are then split into subarrays. Ultimately, the data itself sits in a two-dimensional array of bit cells called a mat, and because there are so many mats, this is where the majority of the logic lies, especially the sensitive logic with little drive strength. It's likely that each mat holds a single logically contiguous byte of data, so as to be able to enable or disable each byte separately for masked DRAM writes. Thus, any mat local errors will manifest as either bit or byte errors, and these two error patterns make up the vast majority of the errors we observe. The baseline ECC that we compare against is SEC-DED protection on each memory entry using 4 code words. SEC-DED stands for a single bit correcting and double bit detecting code. The use of such ECC is common, and GPUs purportedly use SEC-DED protection for DRAM. The decoding behavior of a SEC-DED protected memory entry is as follows. In the case that an error has at most 1 erroneous bit per code word, it is corrected. Otherwise, if any of the 4 code words flags a detectable yet uncorrectable error, or DUE, then a DUE is reported for the whole memory entry. Finally, if no code word flags a DUE and any of the 4 code words has data corruption following ECC decoding, the result is silent data corruption. This SEC-DED scheme is straightforward and has an efficient hardware decoder, but it lacks byte error correction and it suffers from high SDC risk in the presence of byte and beat errors, since these errors manifest in a single SEC-DED code word. Due to the lacking SEC-DED protection against multi-bit errors, we explore the ECC design space using 3 complementary optimizations that are inspired by prior work. The first is code word interleaving, where the code words that make up each memory entry are interleaved in a checkerboard pattern to spread each byte or beat error among all 4. This increases the chance that at least one code word will flag a DUE, avoiding silent data corruption. The second optimization we call the correction sanity check. The way it works is to only allow correction to proceed if all corrected errors are in a likely pattern, such as in the same pin or same byte. Otherwise, the correction sanity check reports a DUE, even if the ECC otherwise thinks that it can correct multiple code words. This sacrifices a scant amount of opportunistic correction for unexpected errors, such as arbitrary double bit errors, but in return it greatly reduces the SDC risk, especially for whole entry errors. Finally, we consider a third optimization, which is to change from SEC-DED protection for each code word to an ECC scheme that can correct aligned 2-bit errors. As we will show later, this optimization has high SDC risk if used alone, but when it is combined with the SDC risk reductions from the first 2 optimizations, it results in a compelling error code. These 3 optimizations are complementary, and we focus mainly on 2 possible organizations. We call the combination of the first 2 optimizations duet ECC, and the combination of all 3 trio ECC. The hardware implementation of a SEC-DED ECC decoder, as well as the additions necessary for duet ECC and trio ECC, are shown on this slide. New or modified structures are highlighted in yellow. At the top of the figure, you can see the wiring that is necessary for the interleaving optimization that applies to both duet and trio ECC. On the left, you can see the 4 original SEC-DED decoders. On the right, 4 new H-column match circuits to localize errors to 2-bit symbols for trio ECC. And then at the bottom, the output formation logic is modified to perform the correction sanity check. Our decoder is designed to support dynamic switching between duet ECC and trio ECC by respecting or ignoring the 2-bit error location signals. We do this because duet ECC and trio ECC expose a correction versus SDC risk trade-off between each other. Thus, by designing the decoder to support both, the user or system administrator can choose to prioritize error correction to reduce the error-related crash rate, or detection to avoid silent data corruption. An alternative baseline we consider is to perform single byte correction using a Reed-Solomon code with 8-bit symbols. This can provide single byte correct using 2 bytes of redundancy. The decoding steps for this alternative baseline are as follows. First, 2 syndrome bytes are generated using fully parallel Galois field multipliers. Next, error location is performed using the pair of syndromes. This can be done efficiently in the case of single symbol correction using discrete logarithm logic and a modular subtractor. Finally, the error location and the first syndrome byte can be used to correct a single byte error. Because we have 4 bytes of total redundancy available per HBM2 memory entry, we can protect the memory entry using 2 single byte correcting code words. Similar to the SEC-DED scheme we described previously, this 2 code word organization is also amenable to the interleaving and correction sanity check optimizations. However, as we show later, the SDC risk of this baseline is high, even with these additional optimizations. In the paper, we describe a novel modification to the single byte correcting ECC that is able to perform single byte error correction with very good multi-byte error detection. We call this scheme SSC-DED for single symbol correct, double symbol detect, and more. The way that SSC-DED works is to augment the single byte correcting ECC code to produce 4, not 2 syndrome bytes. Next, error location is performed not only with the first pair of syndrome bytes, but with each contiguous pair of syndromes. In the case of a single byte error, these 3 error locations should agree, and if they disagree, SSC-DED reports a DUE, avoiding any risk of silent data corruption. This heuristic approach to multi-byte error detection is conceptually similar to the correction sanity check. By checking for agreement between the 3 syndrome pairs, SSC-DED is able to detect all 2-byte and the vast majority of 3-byte errors without resorting to the expensive traditional way of performing multi-symbol Reed-Solomon error detection and correction, which requires the decoder to solve a system of polynomial error locator equations. By avoiding this expensive algebraic decoding procedure, SSC-DED is able to operate using an efficient single-cycle decoder. Having described the baselines and a variety of possible optimizations, I'd like to spend the next few slides looking at the per-pattern ECC behavior of the different codes. In these slides, NI is used to denote non-interleaved ECCs, I is used to denote the interleaving optimization, and CSC represents the correction sanity check. For instance, duet ECC can also be written as I SEC-DED plus CSC. First, let's consider the SEC-DED protected baseline. This code provides single bit and pin correction and double bit detection, but it has significant limitations in the presence of multi-bit errors. The SDC risk is high for multi-bit errors that affect a single code word. This includes both the common byte errors as well as single beat errors. Interleaving improves the SEC-DED baseline by providing perfect byte detection as well as improved beat detection. Furthermore, the addition of the correction sanity check improves the beat and whole entry error detection by 2 more orders of magnitude. This means that duet ECC is able to provide perfect byte detection and very good beat and whole entry error detection with just a 0.0013% SDC risk. The 2-bit symbol error correcting ECC alone has poor performance with prohibitively high SDC risk. The SDC risk of this scheme is even higher than that of the SEC-DED baseline. However, it is the complementary combination of all 3 optimizations that makes trio ECC attractive. Interleaving and the correction sanity check cancel out most of the SDC risk from 2-bit symbol error correction. leading to a scheme that can correct byte errors while maintaining a 78 times better beat and whole entry SDC risk than a SEC-DED ECC. Finally, let's look at the per pattern error behavior of the symbol-based codes, including SSC-DSD+. Single symbol correction has prohibitively high 2 and 3-bit SDC risk, even using the interleaving optimization. Our improved SSC-DSD+ ECC shows very strong performance, however, achieving the lowest overall SDC risk across the board while maintaining byte but not pin error correction. These ECC behaviors lead us to propose two best organizations that differ in their SDC risk, pin error correction abilities, and hardware overheads. We have hardware synthesis results in the paper that demonstrate that both Duet/Trio ECC and SSC-DSD+ decoders can operate within a single GPU cycle, but the SSC-DSD+ decoder is 4 times as large and has twice the delay. Weighing by the error pattern probabilities from our model, we can estimate the overall impact of ECC given a random erroneous memory entry. This slide shows the corrected error percentage. By correcting byte errors, SSC-DSD+ reduces the uncorrectable error probability by 7.44 times over SEC-DED ECC. With its byte and pin correction, Trio ECC leads to a slightly higher 7.87 times reduction. Note that pin error correction is also desirable for permanent errors because it is a common permanent failure pattern, but those advantages are not present in these soft error results. The SDC benefits of our improved codes are even more notable. The optimizations we consider provide multiple orders of magnitude improvement over the SDC probability of SEC-DED ECC. Trio ECC reduces the SDC risk by about 749 times. Duet ECC increases this to a 4,777 times reduction, and SSC-DSD+ is very safe, offering over a 727,000 times reduction. Ultimately, our results serve as an example of a design flow to continually monitor and improve the efficacy of DRAM ECC. We use radiation testing to observe soft errors, perform a detailed analysis to extract error patterns and rates, and then tailor the DRAM ECC through novel error codes that can detect or even correct the most prevalent multi-bit errors. Thank you for listening, and I welcome any further questions you have about this work.